Hello everyone. Hopefully you can hear me well in this screen recording. This is going to be a conversation on runtime analysis and Big O, and will hopefully be a supplementary recording of what we covered in class. So the conversation is highlighted right here. Now I'm going to kind of switch back and forth between Word here so we can type out explanations that you can read. I also have here a little drawing program and a tablet that I'm going to go ahead and use in case I need to draw anything on the screen for you, as well as some images to show you during this conversation. This is probably one of the biggest conversations in a data structures class, right? Big O's can be a very confusing subject for students. First thing we need to know about is a runtime function, right? So here I'll go ahead and give you some runtime function t of n, okay? We'll set this equal to, let's say, 5n plus 3. Once again, we need to define for this function what is our input and what is our output. So calling our conversation from before, our input to this function n is the size of the input to our algorithm. The output here, which is 5n plus 3, represents the work done by our algorithm. Okay. And our job here with our runtime analysis is to first be able to come up with this function that represents the work that's done in our code, and then be able to argue about whether our algorithm is quick or slow at that time. Okay, so this is all about efficiency. So how do we measure efficiency? Question mark. By the way, apologies for any typos I have in this document. So there's a couple ways that we can do this. The first is we go ahead and we talk about time versus space. Okay, so what I mean here is we have time efficiency. This is often also called complexity. And your time efficiency represents how fast an algorithm runs. Your space efficiency is how much extra space, or complexity is how much extra space your algorithm uses. So how much extra space is required by an algorithm. And notice I say extra. Obviously, if you're passing an array into an algorithm, you're already wasting, or not, maybe not wasting, but using some space in memory. Okay, so we can compare our algorithms based on the time it takes, meaning how fast does an algorithm run, and then how much space does it use. Also, we can base our efficiency on inputs. What I mean by this is, given a certain type of input, we may want to look at the worst case scenario, right? So for a certain algorithm, what's the worst type of input that I could hand it? So for example, what about, let's go to the next line here. What about sequential search, right? So with sequential search, the worst case, of course, is going to be that the element that I'm searching for in my array is either not in the array that I pass to the function, or that it's the last element in the array. And so in the worst case scenario, we want to be very pessimistic. Oh boy, pessimistic. Yeah, it doesn't look like this is going to help me here with this, but apologies on my spelling here, but we want to be very pessimistic. We want to be very Debbie Downer. We want to always assume that the worst type of input is going to be handed to our algorithm. So in this case, with sequential search, we're going to have to search through all of our elements from the lowest indices to the highest indices, and in this case, look through our array. And so this is the worst type of input, and this is typically the most common case that we want to look at, the most useful case. We're typically only concerned with an algorithm when it's running in the worst case. We can also look at the average case scenario. So on average, how much work is going to be done with our algorithm. This can be a little difficult or more difficult to calculate, okay, but still useful. Okay, so calculating the average case. And then you could have the best case scenario. And for the best case scenario, this is where we have an input that's going to represent the least amount of work. So if we come back to sequential search here, sequential search, this of course is going to be the case where my search value is going to be the first value in my array. And so I'm going to do as little work as possible. I'll search for that first element at the first index. That's the element I need. Return that index, and I'm done. So this is a very optimistic way to look at an algorithm, and this is actually the least common way to perform or to measure the efficiency in our algorithm. It's often not useful to just know that in certain cases our algorithm will run very fast, because typically our users expect that our algorithms run fast. It's usually when they run slow that our users are going to have a problem and maybe not want to use our algorithm. Okay, so one, we're always going to look at the worst case scenario. We're going to do that for all of our conversations in the future. And then we're typically going to focus on our time efficiency. How much work is actually done with our algorithm? How long does it take to complete? We've talked about this before, but time is an unreliable measurement, meaning that I can't just take two algorithms that I want to see which is the quickest and run them both on my machine and see which completes first. We talked about how there are issues with trying to measure algorithms in this way. For example, what about the speed of a processor, which can affect this, right? If I run an algorithm on a faster machine, obviously the algorithm should run quicker than on a slower machine with a slower processor. What about other processes that are running at the same time? We talked before about preemptive scheduling on a CPU, and how because processes can be interrupted by other processes, this is really an unreliable way in which you try to measure algorithms. You don't know whether your CPU at any one point is going to give you the same amount of time on it from one run of your algorithm to another run of your algorithm. So one time your algorithm you wrote may be interrupted several times, and other processes may be using up a lot of your CPU time. And then a second run that you may perform on your algorithm may get a lot of time on the CPU. And so in either case, time is unreliable, so we can't use this. So really what we need is, like we said before, if I come back up here, we need this runtime function, which counts the amount of work. And then what we want to do is we want to somehow argue about how fast an algorithm is compared to other algorithms. So how can we compare algorithms? Question mark, right? For every new algorithm that we create, somebody is going to wake up tomorrow morning and come up with a new algorithm to which we could compare our algorithm, and it becomes difficult. In fact, it's impossible to consider every type of algorithm. We can't do that. That would take too long. There's always a new algorithm that's coming about. So instead what we want to do is we want to go ahead and let's highlight this a little bit. But instead we want to group together algorithms based on their relative behavior, and we'll group them by what's called their growth rate. Okay, how do algorithms grow, or how do their runtime functions, which represent the work done in that algorithm, how do those grow? And this is also called the asymptotic behavior of the algorithm. Okay. And to do that, we need to, of course, know our functions. I've got a nice image here that kind of shows how some of these functions would look when graphed together. We're going to kind of come back to this function. Notice here on the right side I have several functions, right? I have a log function, a linear function, n log n. You'll see a lot of that this quarter. This may not be familiar to you if you've just taken a pre-calc class. Here's n squared, here's 2 to the n exponential and factorial. Now remember, for each of these algorithms, your n value, or your x, what's typically your x value, right, on the bottom axis here, represents the size of your problem. So here we have up to 100 elements. Obviously, we're concerned about much larger inputs than that, but here you have your elements are growing to the right, and then the height of any point on these curves is going to represent the work that's done. So if I handed an input of 90 elements to a function, a runtime function n, which represents one algorithm and the amount of work it takes to complete, we're going to get about this amount of operations. Not too high. It looks like this lies about at 100 operations on our y-axis here. Notice here though, if I come over and I give the same number of inputs even to just n log n, you're going up to about 600 operations. And of course, going up to n squared is going to be way more work that's done for these algorithms. Each of these algorithms are asymptotically these runtime functions are very dissimilar. They're in complete categories of their own, and what we'd like to do is be able to group these together and see see in general how we can hopefully draw some differences between these. One, how can we show whether one of these is quicker than another? These are graphed very simply here and show some drastic differences, but how can I take, you know, any function that I get and apply it here? Notice if I come back to my function t of n up here, this isn't just a simple linear function. We have, of course, a constant out front here and another term here. So how do we apply that? Well, let's start off with the simplest definition with the of big O. Okay, so the way in which we're going to compare our elements and group them together is using big O notation, which is the primary topic today. Okay, and I want to start by giving the mathematical definition for big O, and it looks something like this. We say that two functions, f of n and g of n, we say that f of n is big O of g of n, which is denoted like this. This is just a big O of g of n, if there are positive constants c and k such that f of n is less than or equal to c times g of n for all n is greater than k. Okay? Now, if you've taken any high-level mathematics courses, this type of definition will look a little more familiar to you. Okay? If you're seeing this for the first time, this can be a little difficult of a definition. What this is saying, though, is at some point, so actually let's put this here. This is the colloquial definition, user definition, less math. At some point, for values, let's say for inputs to our algorithm, larger than k, k is just some constant, f of n will be no slower than g of n within a constant factor. You know, a couple things here. Recall that in this definition, f of n represents the work that needs to be completed in the algorithm that we're writing. Okay, we're interested in saying our algorithm, f of n, or the runtime function for our algorithm, f of n, is big O of this other algorithm. Okay, and what this is going to do is we're going to say that our algorithm runs no slower than the work done in this other runtime function. Okay, so for example here, using our function t of n above, notice, remember, if we come back here, notice I'm using different letters here, but we said, let's assume that we wrote an algorithm and T of n here represents the runtime function for that algorithm. In that case, I could say this, that T of n is big O of n, meaning that my algorithm is going to run no worse than another algorithm that has a runtime of n here within a constant factor. Okay. Now I know when I was first told that, I wasn't quite sure what that meant. A couple key concepts here is g of n is an upper bound for our runtime function f of n. Okay. What I mean is our algorithm will run no worse than the algorithm with a runtime of g of n. Okay. And I've got a nice image I can show you here that kind of highlights this. If I go here and highlight this, this is the same picture that was drawn for me on a board when I took an algorithms course. Okay, notice we have g of n and f of n here. Notice that now remember, our x value here, or n value, right, on the x-axis here, is going to represent our input size. Our y value is going to represent the work that's done. And notice here for small inputs that our y value may differ. Okay, notice that if g of n represents some runtime function for some function, and f of n represents the runtime function for my algorithm, then in that case, notice that for small inputs, the amount of work that's done differs for either of these algorithms. Notice at one point, my algorithm may take more work, and then at another point, this algorithm that's modeled by g of n may take more work, and it goes back and forth. But after this point k, this is why we have this point, this constant k, for any input that's larger than k here, my algorithm, notice the amount of work that it takes to complete my algorithm will never be worse than this other algorithm that's represented by g of n within a constant factor. There is a constant here, but still, notice that this blue line here represents an upper bound on the work that's done in my algorithm. Okay, and the way I like to describe this is to describe, and I already shared an example like this with you, is, imagine I'm at a software company, and I know a person on my team, let's call this person Bob, and let's say Bob wrote a searching algorithm that is kick-ass, and in general, we'd call it a fast algorithm, okay, whatever that means. We'd say we like Bob's algorithm. It works well. It's fast. It doesn't use up a lot of space. We like the way Bob's algorithm works. So I then, Josh, go away into a cubicle somewhere, and I try to write an algorithm that's better than Bob's algorithm, and let's say I'm successful. Okay, so I write another searching algorithm as trying to improve upon Bob's algorithm, and in the end I discover that my algorithm is faster than Bob's. Well, if I then say that Bob's algorithm is an upper bound for my algorithm, or the amount of work that's done in my algorithm, then what I'm saying is my algorithm will run no worse than Bob's. But that's actually saying something that's pretty good, right? If my algorithm is no worse than Bob's algorithm, then mine's pretty quick, because like we said before, Bob's algorithm is quick, okay? And we need to be a little careful here, okay? If I say that my runtime function, for example, T of n, is big O of n, well, if we're trying to compare my function against a linear function n, linear here represents one of the better runtimes that an algorithm can take on. Meaning, if I come back to this original comparison chart, okay, and pull up each of these algorithms, remember the height of each of these curves represents the amount of work that's done. Notice that down here at the bottom is our linear curve, and notice that for larger inputs, you're going to have a reasonable amount of work that's done down here. Notice this is not growing very rapidly, at least compared to n squared or 2 to the n or even n factorial, which is really bad. But all of these grow rapidly. But notice the linear function is down here, and it's not a bad algorithm. So if I say that my function, t of n, which represents the work in my algorithm, is big O of n, I'm saying that within a constant factor, my algorithm will be no worse than an algorithm that's represented by this linear function. And because of that, my algorithm is pretty quick. But here's the thing, I can actually say things like this. I could say that my algorithm is also big N of, let's say, n squared. Or I can say my algorithm is big O of 2, let's say 3 to the n, to some exponential function, okay? In these cases, we know, if you've studied big O a little bit, that these represent actually bad runtimes. These are both very, for very small inputs, these algorithms take a lot of steps to complete. There's a lot of work to be done. And in general, given even small inputs, it takes too long for these algorithms to complete the amount of work that they do. Okay, so these are generally considered inefficient. So if I say that these are an upper bound for my runtime, that's not actually saying much. If I say my algorithm is no worse than this really slow algorithm, I'm not saying a lot about my algorithm itself. And so what we'd like to have is what's called a tight upper bound. Okay? So when I say t of n is no worse than n, that's actually a tight upper bound. These other functions are not a tight upper bound. Okay? So a couple of things. How do we get this tight upper bound besides using this really terse mathematical definition? Because in general, we're going to try to avoid some of this mathematical notation. So a couple of things here. We're going to use some simplifications to determine the big O for our runtime functions. Okay. Let's make this here. So this is what we're going to do. All right, first things first. Given a function t of n that represents our runtime, let's say it looks something like this. The very first thing we're going to do, rule number 1, is we're going to only consider leading terms. Okay. And when I say leading terms, I mean dominant terms. Okay, so what I mean here is that our term here in this function, 7 of n, is completely dominated by this first term. If you don't believe me, go ahead and give an input to this function such as, let's say, t of 1,000. Now remember, 1,000 represents the size of our input. So we have 1,000 elements that we're sending into our algorithm here, and this is going to result in this amount of work. Notice here how much that first term dominates the amount of work that's done here. Here you have 7,000 steps in our algorithm. Here we have 16. This becomes so dominant that what we're going to do is we're going to completely ignore this non-dominant term. We're going to pretend it's not there. And it's not going to have a large effect on our algorithm because most of the work that's done in our algorithm is going to be represented by this leading term. If you don't believe me, increase your input size here. Okay, and notice that indeed this has almost no effect on the work done as our input size gets larger. Okay, and this is actually highlighting an important principle. This is going to be a principle throughout our conversations here, and that is we're only going to consider large n. We only are worried about when n gets very large. And if you come back up here to the mathematical definition, that's kind of represented here. Notice here, I'm only concerned about when n is larger than k at some point. So if I come back here to this original image, I didn't really care what happened before this point with k. I didn't care whether these, whether the amount of work differed between these two functions before we get to this point k. But after this point k, my concern for very large n is that it's never the case that f of n represents more work than another function g of n within a constant factor, okay? So if I come back here, we're going to ignore this, and we're only going to consider large n here, and that I think makes sense when you look at this example. Okay. The second thing I'm going to do is I'm going to ignore. I'll make this rule number 2. I'm going to ignore leading constants. What I mean is that if I have my function t of n here equals 7n plus 16, I'm going to both ignore my leading constant, and I'm going to ignore my my non-dominant term there. Okay, and once again, if we come right back once again to our mathematical definition here, notice that I allow f of n and g of n here. Recall that this is the runtime function that we're using here. This is basically t of n. These functions that we're using here can differ by a constant here. We're not going to pay attention to this constant. And it may seem like that will have a large effect on our runtime here, but it turns out it won't. If I come back here and take a look at, take a look at these different classes that I have here, okay? Any linear function that you have, whether or not it differs by a constant, all of those linear functions are going to be down here for large n, okay? These other functions such as, n squared or my exponential function, as you zoom out in this graph for larger and larger inputs, there's always going to be a drastic difference in terms of these functions. So I'm going to try for the first time to draw on my pad here, and bear with me here, okay? But if I go ahead and, let's select the pen over here. Here we go. If I go ahead and, oh boy, here we go. I'm going to do my best here. And draw my graph here, okay? If I go ahead and draw up here, f of n, oh boy, here equals 2 to the n, okay? That's my exponential function. And then I draw a linear function over here, okay? All of these linear functions are going to be very close to each other, okay? So perhaps this is, I don't know, f of n equals, let's say, 7n. Maybe this is f of n equals 5n, and so forth and so on, okay? So the point here being is that these functions are going to be, pardon the drawing, sorry, but this isn't the greatest drawing ever, but these functions are going to be far down here. In fact, in the long term, and hopefully I can draw this a little bit quicker here and go ahead and cut all this out. But if I go ahead and draw this again, if I was to zoom way, oh boy, lost my pen there. But if I was to zoom way out on this graph, so I can imagine that this is for your scale here is much larger. Your exponential function is going to look like this, and your linear functions are going to be way out here, and they're all going to be roughly in this area, whereas all your exponential functions are going to be up here. So there's a drastic difference between these two. These are nowhere even close. But what I don't care about, I don't really care about whether there's small differences here. This is why we said that this was a conversation on growth rates, right? My main concern is this drastic difference here between these two functions, okay? I want to know about big categories. And it turns out that using this notation, okay, after I've gone ahead and apply these two rules, I ignore my dominant terms and I ignore my leading constants, I can end up then saying that whatever is left is what my big O is for my function here. So in this case, I would say t of n is equal to big O of n. So once again, I could let's go ahead and apply a new function. So let's say I have a new function t of n here, and let's say this time it's 16n plus 21. Once again, what are we going to do here? We're going to go ahead and ignore our constant, even though it's different. And the last one we saw, ignore a non-leading term. And in fact, let's give this a different name. We don't always have to use t of n, but notice here I can say in this case, g of n is equal to, once again, big O of n. In fact, I can keep doing this. Let's say I have a function h of n that represents the runtime of another algorithm. I could say this is 100n plus log of n. Now you're probably wondering in this case is which of these is the dominant term? It turns out that indeed n is going to dominate this term on the right again, and I'll argue in a little bit about why that's true. But we can once again ignore this, and for each of these cases, we can say that all of these, h of n here, and g of n, and t of n are all big O of n. Notice that they have the same big O. So what am I arguing here? With this big O, I'm trying to argue that roughly speaking, within a constant factor, all these algorithms run at roughly speaking the same speed. Okay? What I mean is they're all out here in roughly the same area. Okay? There's a huge difference between these algorithms and another algorithm asymptotically, okay? And so what we can do by using this notation, is we can group together algorithms into certain categories. Let me give you a few other functions just to show you how this may work. So let's try a few others that may fall into other categories. So let's redefine t of n here, and let's say this is n squared plus 16n, maybe something like that. In this case, once again, I'm going to say that t of n here would be big O, in this case, of n squared. Why? My n squared term is going to be my dominant term, so I'm going to ignore the non-dominant term. There's no constant out here. If there was, I would ignore it. Let's try this again. Let's denote a g of n here, and I'm going to give you another function. Maybe this is 10 times n squared plus 2, okay? In this case, once again, in fact, maybe you don't even have the plus 2, or maybe it's just 10n squared. I'm going to ignore that leading constant, and I would say g of n is big O of n squared. Notice how I'm sort of saying, these have different runtimes. There are differences in the speed of these algorithms, but even though they're different, I can group them together into one big O category. So you're probably wondering, what do these categories look like? How many categories are there? Well, there's a bunch of popular categories. Typically, if you're reading a book on algorithms, they'll give you a set of efficiency categories that looks roughly like this. Okay. Notice you'll see a couple familiar ones in there. We were going over big O of n category or algorithms. Notice here is big O of n squared. So let's go from the top to the bottom. So you're probably wondering what big O of 1 is. Okay, that's what's called constant complexity. Anytime you have a runtime function, let's go down a little bit here. Let's say t of n equals 16. So recall this is a constant function. This means that my work done in my algorithm is not dependent on my input size, which is n. Okay, but whenever I give a big O of a function like this that's constant, we always say it's big O of 1. Okay, so remember, we ignore these constants. Okay, so if I had that, I would say that's big O of 1. If I had g of n equals 10,000, but once again, it's just a constant, I would say that g of n equals big O of 1. Why? Because for any other function that's dependent upon n, eventually I can give a large enough input size that will dominate this term. So even though this may seem like a big constant, we're still going to ignore that. Okay, so both of these would be big O of 1. That's something you'll have to memorize, and that's this first category. Okay, and by the way, we are going from the top here are our fastest algorithms to the bottom, which are our slowest algorithms. Okay, the top here represents the least amount of work. The bottom represents the most amount of work, and we'd want to stay near the top here, okay? All right, so next is log of n. We're going to go over some tree structures in a later video, I'm sure. Tree structures have logarithmic behavior, so binary search trees, balanced binary search trees, heaps, exhibit this logarithmic behavior. Then we have linear complexity. So falling into this linear complexity would be algorithms such as sequential search. Right? So if you recall, for sequential search, as we said before, in the worst case, sequential search is going to be big O of n. Why? Because in the worst case, we have to search all the way to the end of an array to find an element in that array. So big O of n. We'll see n log n pop up this quarter when we talk about sorting, or in a later video on sorting. And then you have polynomial complexity. So just to be clear here, notice how I grouped together polynomial complexity here on the right. Each of these categories are not the same category. When I say n squared, n cubed, n to the fourth, and for any k, as k gets larger for each value, each of these belong in their own big O categories. So n squared is faster than n cubed, which is faster than n to the fourth, okay? And all of these are going to be slower than our exponential category, which notice here the bases change, and once again, for any base k, these are going to be in their own category as k increases. And then you'll have other kind of extreme categories, n factorial. We'll see some algorithms at some point that exhibit this exponential or factorial behavior. But in general, for an algorithm to be efficient, we want to be up here above n squared. Okay, once you drop below this n squared threshold, so if you're n squared or below here, what you're going to need to do is begin limiting the size of the input to your problem due to the amount of work that your algorithm is doing. Okay, so in general, efficient algorithms lie above n log n here. Okay, anything below, you're going to have to begin performing some tricks to speed up your algorithm. Okay. All right, so I wanted to mention one other quick note before I pause this video and give you a second to take a break before we cover a couple other subjects. But one thing I wanted to show you, and that is there's another important rule here in terms of logs that should be stated, and that is each base for a log function, which represents the work of an algorithm we created, belongs in the same big O category. Okay. So let me just be clear here, and this may be a little hard for me to do in Word here, but if I have, let's say that at one point here I have that that the work for my for one algorithm I write is represented by 6 times the log base 10 of n. Let's see if I can drop this down here. So log base 10 of n. Okay. We would say that this is big O of log n. Okay. Notice here that I'm ignoring my constant, and I'm also ignoring my base here. Okay. And this is true for any base. So if I had another function, g of n equals 100 log base, let's say it's the log base 2 of n plus 100, or 1000, something like that here, I would still say that this function is big O of log of n. Notice I don't even specify the base. My argument here is that every base, each base, belongs in the same big O category. Okay? And that may be a little hard to swallow at first, but you can actually show this using the change of base formula. So we can show this using the change of base formula, which we all forget and then recall, in our classes when a teacher reminds us of this. Okay? So let's say that I had let's say I had some function, any function. We'll call this the log base k of n. And I want to change this to, let's say it's the log base 2 of n. Okay, so to do that using the change of base formula, we would write a statement that looks like this. This is actually the log base 2 of n divided by the log base k, the log base 2 of k. Okay. Now, just to be clear here, this is actually equal to 1. 1 divided by the log base 2 of k times my log base 2 of n. Okay, and the argument I'm going to make here is that this left side is just a constant, right? So a couple things. 2 is just a constant, but what is k? K was the previous base here. This was the log base 2 of n, or e of n, or 10 of n. Whatever the base is here, this is typically a small positive constant. So because of it, this is a small constant, this is a small constant. 1 divided by the log of a small constant is just a small constant. All of this is just a constant. Because of that, because I can say that my log with the base k is equal to the log base 2 times some small constant, this is actually showing that these lie in the same asymptotic category. Why? If I come back up to my mathematical definition, recall that we said we ignore constants. We ignore the constant difference between two functions when we're applying a big O argument. So we ignore those constants. Remember, if I come down below here, what did we do? We ignored the constant difference between my runtime function t of n and another function that may have that constant out front. So we ignore constants. Because of that, we can ignore this. And what does that mean? In big O speak, the log base k of n is considered to be, roughly speaking, within a constant factor in the same big O category as the log base 2 of n. Okay? So this quarter, we're going to ignore the base of logs, essentially. Okay? We'll mention them as they're pertinent to parts of our conversations, maybe in a later video. But in general, we're going to not pay attention to those. All right, so I'm going to go ahead and pause the video here. This is a good stopping point real quickly to kind of catch your breath, maybe go back and relook over this video. We're going to continue this in a moment and talk about big omega and theta and a couple other notations that are related to big O. So go get a glass of water, some fresh air, take a moment, pause the video, and we'll be right back. All right, everybody, welcome back. Hopefully you had a chance to take a breather there. Let's see if we can wrap up our conversation on big O here. We're going to kind of use this notation throughout our conversations and these videos in this quarter. So the next set of notations I want to show you, which kind of follow under the same big O notation, is I want to define what's called big omega, okay, which is related to big O. So related to big O. So here, I'm going to give you the definition here. And in fact, you might find this a little funny, but I'm going to come up and I'm going to copy this mathematical definition here because the definitions are very similar between these. So for big omega, this is the mathematical definition. We say that f of n is a big omega of g of n, denoted here that f of n is, and here I'm going to go ahead and see if I can find the symbol omega here, which I think is right down here. Hello, help me out here, Mac. There we go. So we say that f of n is, this little horseshoe means omega of g of n, if there are positive constants c and k such that this is the case, that f of n is greater or equal to c times g of n for all large n. So what does this mean? Does this mean? Okay. So a couple things here. F of n is the runtime function of our algorithm, once again, like our big O definition above. This says that g of n is a lower bound on our runtime, on f, let's say it this way, for f of n. That's probably the best way to say it. Okay. What does this mean? This means that our algorithm will run no better, read always at least as worse, or as bad in terms of the amount of work that's done as g of n. Okay? Good way to denote that, if I come back over here and clear out some space here, grab my tablet here, and here we go. And once again, oops, let's get my little drawing pad here. Draw my grid here. What does this mean? So I may have, you know, some differing here at the beginning between these two functions, okay? But in this case, now my function f of n is out here. This is my function g of n, okay? And what this means is that, excuse me for the little typo there, what this means is that at some point here, down here, for all n is greater than k, my function f of n that represents my runtime is always going to be worse than this g of n function within a constant factor. Okay, let's see if I can get rid of this. What does that mean? That means that mine's worse than this. It means mine is that this provides the best case that my algorithm could ever run in. Okay, notice here that this is saying greater or equal to this. Okay, this is a great algorithm or a great notation for arguing about a minimum. So this is a great way to denote a minimum amount of work that an algorithm needs to complete. So a minimum. Okay. All right, so that's big omega. We'll use that a little bit. And then we have another notation here, which is called theta, which is also, how did I denote that above? Related to big O also. In fact, all of these are. I can probably leave this off, but let's just go ahead and put this here. Okay. And I'm guessing that you're guessing probably where I'm going with this. So let's give the mathematical definition here. So we say that f of n is, excuse me, this is big theta, or just theta. You can just say theta here as well. But we say that f of n is big theta g of n, denoted f of n is equal to, let me go find my, hopefully I forgot to look for this one early. Hopefully I can find this quickly here. I'm gonna stick with, I'll stick with this. This will be good enough. So that's theta. So we'll say that is big theta g of n. So this is, I'm going to type IFF here. This means if and only if. Okay, just a little bit of math speak there. If and only if f of n is big O of g of n, and g of n is big O of f of n. Okay. All right, so this is typically takes a little bit to sink in here. So recall kind of what does this mean? So f of n being big O of g of n, that implies what? That roughly speaking, f of n is going to be no worse than g of n within a constant factor, roughly speaking, right? My algorithm, f of n, is going to take less work than g of n, or it's possible that it takes the same amount of work. Notice the equal sign here. Okay, the other thing this says, the second, this second part right here, right? So in fact, let's highlight these just to make this crystal clear. So we'll highlight this first one in, let's say, orange. So here I have orange. We'll highlight the second part in, let's say, blue or something. Okay. So the second definition here, which I'm going to click here, says that g of n is big O of f of n. Therefore, we know that g of n is less than or equal to f of n within a constant factor, meaning that this function also will be no worse than the work done in this function. But here's the thing, guys, okay, is that for both of these inequalities to be true, it must be the case that this is true. And I'm getting into my code here, right? But it must be the case that f of n and g of n are roughly speaking equal. So roughly equal, meaning they take the same, or they, let's say it this way, they represent the same amount of work within a constant factor. What does this mean? They have the same growth rate. Okay? Or they lie in the same category in terms of growth rate. Okay? Now, if I come back above here, this is what I was arguing when we had several functions and we simplified our functions and we kept getting big O of n, big O of n. In fact, these three functions that I've given here, I guess some of this is on the page before, but these three functions are all theta of each other. It can be shown that t of n and g of n and h of n are all big theta of each other. They lie in the same category. They all have linear running time. Okay, coming back here, they all lie in this category right here, in the linear complexity category. Okay, so I can say, using this notation now, that if my algorithm is big O of another algorithm, that mine is no worse than that. I can argue that it's big omega of another algorithm, which says mine's is always at least as bad as another algorithm in terms of time. And I can say that two algorithms lie within the same category. Okay. And I'm going to quickly allude to two other types of notation as we kind of wrap up our conversations here. And that is, there's two other notations, which is little o and little omega. And I'm just going to quickly allude to what these are. Okay. And I'm not going to give the mathematical definition here. But what these means are, what these represent, so if I have little o, this represents that, you know, and you could derive the mathematical definition up above, but this means that f of n is less than, strictly less than g of n for large n within a constant factor. Okay. So this is kind of similar to big O, but you're saying something more. Recall that big O said that f of n is less than or equal to g of n. This says it's just less than g of n. Okay, so in this case, you're saying that my algorithm is no worse than well, you're actually saying that your algorithm is better than g of n in this case. My algorithm represents less work. G of n is an upper bound, but mine is not going to be in the same asymptotic or growth rate category as g of n. Okay, that's kind of the cliquel way you want to think about that. Here also, for little omega, we're roughly speaking, we would say f of n is going to be greater than g of n, meaning that, well, first, this is for large n within a constant factor. Okay. So what does that mean? Here we're saying that my algorithm is always going to be worse than g of n, not in the same category. Mine is always strictly worse. So mine's going to be in a different growth rate category than whatever g of n is. Okay. Generally speaking, we're going to avoid these two definitions and stick with big theta, big omega, and most importantly, big O. Recall that, you know, for big O here, there's a lot we can say with this. Most of our arguments this quarter are going to be somewhere along the lines of, I know a fast algorithm. If my algorithm is big O of that other algorithm, then that means my algorithm is fast also. Okay, so we're going to stick mostly with big O this quarter and through these videos as you take a look at them. A couple things here, guys. So just realize, you know, you don't always have to derive your functions, your runtime functions. You can often reason about an algorithm by counting loops. So for example here, let's go through a couple of these code segments that we discussed before. So here, Let's see if I can make this a little bit larger. Let's zoom in here. Notice here I have the swap method that we've discussed before, where I take an array and I swap two elements in that array. This represents obviously a constant amount of work. I'm not looping over my array. I'm not interacting with each element in my array. So if my input size, the length of this array is n, my runtime for this algorithm is not in terms of n. This would be something like t of n equals 7 or 9 or 13 or some number that represents a constant amount of steps that occurs inside of this algorithm. Okay. If I go to an algorithm like linear search here, let's see if this will increase in size a little bit. Hopefully that's a little bit easier to see. What we could do in this algorithm is just quickly reason that this loop is going to loop over our input of size n, and because of that, the steps that are performed in this loop, in the worst case, is going to be performed roughly speaking, n times. Okay. Now notice in linear search or sequential search, the best case scenario is I find my element when I look at my first element in my array, and I immediately exit. The worst case scenario is that this is never true. I look through all my elements, I loop n times through my array, and then I return this -1 bogus index saying that I didn't find my element. Okay, but in the worst case scenario, I can kind of count this loop. If I loop over my array once, then this algorithm is going to run big O of n. Okay, it's going to run in my linear time category while I'm counting my loops once. Okay. Here's another algorithm that we can take a look at. This, excuse me, wrong one. I'm looking for duplicates here. This algorithm takes an array and searches through the array to see if there's any duplicates. And notice that there's a nested loop here that loops over my array twice. I loop over for each element I. I then loop over the same array for each element j. And if I and j are dissimilar, I ask the question, is the element at index I equal to the index or the element at index j? And if that's the case, it's true. Now, once again, the best case scenario is I find that the first two elements are equal to each other, and we only go through this loop a couple times and we return true. The worst case scenario is that I have to go through all my elements in my first loop n times. This inner loop runs n times, meaning that this inner loop will run a total of n steps, but then this outer loop is going to run the inner loop n times. And that'll give you a total running time of, roughly speaking, n squared, n times n. And so you can kind of count these loops. I have one loop nested inside of another loop, so that this is going to be n because of the outer loop times n because of this inner loop, so you're going to get n times n. The worst case running time of this algorithm is going to be big O of n squared. Okay. Once again, this first loop counts as n, the second loop counts as n. We multiply them together and we get n squared. Okay. You need to be a little careful when you're performing steps like this. You may run into, for example, an algorithm that looks like this, which I almost linked to before. Notice here I have two loops, and so some students will jump the gun and say immediately that this is going to be n squared running time, but notice here that I pass a word in, okay, into this algorithm. This algorithm takes a word and tells you whether the word contains your vowels here. But if you want to give a big O estimate of this algorithm in terms of its input size, notice that your input is this string, so the length of the string is going to be our value n. So this outer loop indeed is in terms of n, the length of the string. Notice though that this inner loop is not looping over our input size, our input, our string that's passed to our function here. Instead, it loops through this small array of vowels, okay? And the size of this array is constant. This array will always be exactly 5 characters long. Our string, though, could be 10,000 characters, 30,000 characters. We don't know how many elements or characters are inside of this string. Because of that, this inner loop is going to run at most a constant number of steps. So because of this, would actually be n times the number of times this inner loop will run, which is going to be constant. So we'll have some constant factor times n, and this big O for this algorithm is going to end up being something like big O of n. So it may be modeled something like this, where you get some runtime function. There's a constant number of times that inner function is ran. We multiply that by n. But of course, we ignore that constant in front of our runtime function, and we get a linear running time. So we need to be a little careful here that if you're going to count loops, that your loop is actually running n times. Otherwise, we can't be so bold. Alrighty. So that's big O notation and runtime functions in a nutshell. This takes practice. We're going to quickly shift over to many other algorithms as part of this course in this video series. And every time we interact with a data structure or an algorithm, the second we're done with talking about how that data structure works or that algorithm, we're immediately going to talk about how much work is performed in that data structure and try to give a big O analysis. The goal, of course, is to be able to define large groupings of efficiency, right? I'd like a group of algorithms that are fast, sort of fast, slower, really slow, terribly slow. I'd like to have these categories so that I can have some perspective on whether a new algorithm that I create is fast or slow. And I'm going to compare that against existing algorithms by lumping them into these categories. So one thing you want to just keep in mind is we're constantly going to be trying to define algorithms in terms of these efficiency classes that you see in the picture here. And it takes practice, okay? So you have to kind of go back through this and remind yourself what we're arguing with big O. It's all about me saying my algorithm is faster than this other algorithm. And if this other algorithm is faster, that means my algorithm is also fast. Alrighty, we'll see you next time.